Welcome everyone. Today, we're going to explore a fascinating new hypothesis that suggests a hidden connection between prime numbers, composite numbers, and the golden ratio. This presentation is based on an intriguing video analysis, and it proposes a fresh perspective on the seemingly random distribution of primes. We'll delve into how these ancient mathematical concepts might be intertwined in a way we haven't fully appreciated before. It's a journey into the unexpected structure of numbers. So, the central question we're tackling is, do prime numbers, those notoriously unpredictable integers, actually hide a golden secret? For centuries, primes have baffled mathematicians with their erratic appearance on the number line. But this new hypothesis challenges that view, suggesting that if we look at primes through the lens of the Fibonacci sequence, a clear, measurable link to the golden ratio emerges. Specifically, we're asking if the normalized arithmetic mean of primes within these Fibonacci intervals converges to a fixed constant, precisely half of the golden ratio. It's a bold claim, and we'll explore the evidence for it. To understand this hypothesis, we need to consider its three foundational pillars, each an ancient concept in its own right, now brought together in an unexpected connection. First, we have prime numbers, those integers greater than 1 with only two divisors, 1 and themselves. They are sparse but infinite. Second, there's the Fibonacci sequence, where each number is the sum of the two preceding ones. Its consecutive ratios famously converge to the golden ratio. And third, the golden ratio itself, phi approximately 1.618, a unique constant found throughout nature and art. The hypothesis suggests that Fibonacci intervals act as a natural ruler for measuring how primes and composites relate to phi. Building on those foundational concepts, we now define the specific measurement windows for our analysis, the Fibonacci intervals. The core idea is to partition all numbers into subsets, bounded by consecutive Fibonacci numbers. Formally, for any two consecutive Fibonacci terms, f, n1, and f, n, our interval includes all integers k that are greater than f, n1, and less than or equal to f, n. This half-open interval is crucial. Within each of these defined intervals, we then classify numbers as either prime or composite, and we compute their arithmetic means separately. For example, in the interval between Fibonacci 13, which is 233, and Fibonacci 14, which is 377, we analyze the primes and composites found there. Now, let's look at the core formulas that formalize this hypothesis, showing how the golden ratio acts as a boundary between the means of primes and composites. The hypothesis proposes two key inequalities that together bracket phi. For primes, the normalized mean is always greater than or equal to phi divided by 2, meaning primes approach this value from below. Conversely, for composites, the normalized mean is always less than or equal to phi divided by 2, indicating composites approach from above. This creates a combined bounding relation where phi is always situated between the scaled prime mean and the scaled composite mean. This elegant mathematical relationship is central to the entire hypothesis. We've established the core formulas, and now we see the evidence. Computational results up to Fibonacci 46 reveal a clear and consistent pattern of convergence. For small Fibonacci numbers, the prime and composite means diverge. But as we move to larger numbers, they both approach the golden ratio. This narrowing band, with primes always below and composites always above, is a key finding. It's a directional, asymmetric convergence that strongly supports the hypothesis. Building on the numerical evidence, the visualization provides a powerful visual proof of the convergence. The blue line, representing the prime-based mean, consistently approaches the golden ratio from below. Conversely, the red line, for the composite-based mean, approaches it from above. The golden dashed line is our target, the golden ratio itself. Notice how the shaded band between the blue and red lines shrinks dramatically as the Fibonacci index grows. This visually confirms that the golden ratio is always bracketed by these two means. This convergence is deeply connected to how primes behave in larger number sets. As Fibonacci intervals grow, composites increasingly dominate. This is a direct consequence of the prime number theorem. At smaller indices, primes and composites are somewhat balanced. But for larger Fibonacci numbers, composites can outnumber primes by a factor of 5 or even 10. This growing imbalance is crucial. The prime mean, with fewer and more scattered values, converges from a structurally different direction. This sparsity of primes is a fundamental aspect of their distribution. To test this hypothesis, custom software was essential. The author developed two dedicated applications. POF Spiral was a graphical tool, visualizing numbers on a Fibonacci spiral and marking primes and composites. PAX, a console application, used the sieve of Eratosthenes to compute the necessary sums and means for each Fibonacci interval. However, there were computational limits. The sieve exhausted available RAM at larger Fibonacci numbers, and 64-bit integer limits in C prevented verification beyond Fibonacci 46. These are engineering constraints, not mathematical refutations. The sieve of Eratosthenes, an ancient algorithm, is the computational engine behind this modern hypothesis. It's a remarkably simple yet powerful method for finding prime numbers. You start with a list of integers, then systematically mark the multiples of each prime as composite. The numbers left unmarked are your primes. It's highly efficient for moderate limits, with a time complexity of O(n log n). However, its memory complexity becomes a bottleneck for very large numbers, which is precisely what the author encountered. After exploring the computational methods, we can now draw some firm conclusions. The primary takeaway is that the hypothesis holds true across all tested Fibonacci intervals. We consistently observe that the normalized mean of primes is always less than or equal to the golden ratio, while the normalized mean of composites is always greater than or equal to it. This isn't just a random occurrence. It's a clear, directional convergence. Primes approach from below, composites from above, and the gap between them steadily shrinks. If rigorously proven, this hypothesis would establish a profound, quantitative link between prime numbers and the golden ratio, two pillars of mathematics. It suggests that Fibonacci intervals offer a natural and effective way to study prime density, potentially revealing new patterns. This also prompts us to ask if other number-theoretic functions might exhibit similar convergence to the golden ratio. These are exciting avenues for future research. To encapsulate our findings, the arithmetic mean of primes within a Fibonacci interval, when normalized, converges to half the golden ratio from below. Conversely, the arithmetic mean of composites in the same interval, also normalized, converges to half the golden ratio from above. This means the golden ratio is consistently bracketed between these two scaled means. This elegant relationship, if formally proven, would represent a truly unexpected and significant connection between prime number theory and the golden ratio. Thank you for joining me today as we explored this fascinating hypothesis. We've delved into the potential connections between prime numbers, composite numbers, and the golden ratio, building on the insights from the video analysis. I hope this presentation has sparked your interest in these mathematical concepts and the intriguing possibilities they present. Your attention and engagement are greatly appreciated.